Our first definition is a secant line. So if you have any graph, say a parabola, and you chose 2 points on that parabola, the line going through those 2 points would be a secant line. Now it says usually at 2 points because the secant line might eventually cut through the graph again if it was an x cubed graph, but you would be talking about the secant line between 2 points. So take any 2 points on the graph and draw a line through them, that would be a secant. You may have had the equation of, or the definition of a secant for a circle. That's any line that cuts through 2 points of your circle. Our tangent line is a line that touches a curve at 1 point and usually doesn't cut the curve at that point. So on our parabola, your tangent would look like this. And it would touch that curve just at that point. And the reason I say it usually doesn't cut through that curve at that point is because there are some cases, like the x cubed graph, there is a tangent at 0 that's horizontal, stationary point of inflection. It actually cuts through it, but it's still the tangent at that point. But usually, when we're talking about a tangent, it's a point that touches the curve at that point but doesn't cut through it. So now, rates of change, we consider 2 different rates of change. There is an average rate of change, which is looking at your overall effect on one variable over the other, and that is the slope of your secant line over 2 points. It's like when you figure out how long it took you to drive from here to Portage la Prairie, and you know that it's 50 kilometers. If it took you an hour, you know that your speed is 50 kilometers per hour. Your instantaneous rate of change, that's what your speedometer says at a moment. You're driving on the highway, you look down at your speedometer and it says, you're going 100 kilometers per hour. That's what you're going at that instant. That's not your average speed for over the whole trip, because your speed fluctuates. And your instantaneous rate of change is the slope of your tangent at a point. Now, we use a lot of different notations for rate of change. You've already learned about slope. Another word for slope is gradient. Here's your slope formula, m equals y2 minus y1 over x2 minus x1. This is basically your rise divided by your run. You can write it as change in y, delta y over delta x. And your slope is your first derivative. So that's our connection that we're going to get to into calculus. That our first derivative is the slope of our tangent. So we're going to make up a little story. We're going to put time along our x-axis, time in, we'll say in hours. We'll do distance on our y-axis. Every one here will be in 100 kilometers, so this will be 100, 200, 300. And maybe this is distance from Winnipeg or something like that. So you start off in Winnipeg at time 0. In 1 hour, you get 100 kilometers away from home. Maybe I'll make it a little bit more realistic. You start off slow and you speed up. And then as soon as you're 100 kilometers away from home, you realize that you forgot your wallet at home. Oh, You got to head back home. So you get back home in half an hour. So during that time, you're traveling 200 kilometers an hour. Probably not a good idea. But now you're behind schedule, and now you take off again and leave Winnipeg, and at 3 hours, you were at 3 kilometers. 300 kilometers. Over the next hour, you're stopped. What happened? You probably got pulled over, yes. You didn't forget your coffee at home. No, that would be another thing. And then you just sit and cry in your car for an hour. No, probably you'd get stopped, because if we look at from here to here, and we drew a secant line from that point, can you see that your x value is 1.5? And you've gone up 300. And if you take 300 divided by 1.5, how fast were you going? Right? 200 kilometers an hour. Good idea. Is it reasonable that you got a speeding ticket? Yes. And then after that, you keep driving. Oops, I've gone green. You keep driving in a much more reasonable space. So in between here and here, when we drew our secant line, we could find our average speed over that time. Right? From here to here, what would your average speed be from that point to that point? What's the slope of a horizontal line? Zero, right? The slope of a horizontal line would be 0. Because what's happened from this point to this point? You haven't actually gone anywhere. You did travel, right? You did travel, but you realized you forgot something. You got back to the same spot. Looks like after an hour, you're back to the same spot you were an hour ago, but you haven't actually gotten anywhere in that hour. So your average speed over that time was 0 kilometers per hour, because you would have done just as well had you just stayed there for an hour and said to yourself, what have I forgot? What have I forgot? What have I forgot? And then you would have realized after an hour, I forgot my wallet. That's what I forgot. And then you could go back home. Now, if we wanted to draw a tangent at one of these points, so let's say I choose this point here, and I drew a tangent line, I could see if I could figure out how fast I was going at that instant. I'll make this turn into a nice number. Oh, look, it went right through 200. Perfect. Can you see that you've got a rise of 200 and a run of 2? If I would do 200 divided by 2, I would get 100. And so at that time, if I looked at my speedometer, I would be going 100 kilometers per hour. And that would be an instantaneous, because that's the slope of that line at that moment. Now that slope, because it's going down, would have a negative 100, right? You know that slopes that go down from left to right have a negative slope. In this case, the negative 100 just is telling you that you're going 100 kilometers per hour. You're not driving your vehicle backwards. It just means you're going back home, right? Because the negative is just telling you which direction you're going in this case. So those are basic ideas. As far as, I'll erase some of these. Some of these lines, and then we can actually look at the intervals that are given here. 1, 2, 3, 4, 5. So we can label some points on this graph. This is where it's at 1. At 2, it's right there. At 3, it was up there. 4, it was there. And 5 looks like it's there. So if we have those points, calculate the average rate of change from 1 to 3. So if you went, and we'll do 1 to 3 in red, if you went from this point 1 to this point 3, and you connected those two, your average rate of change would have been 200 kilometers over 2 hours, which would be 100 kilometers per hour. That wouldn't have been bad. You probably wouldn't have had this stretch of time in here where you didn't go anywhere, had you just been traveling 100 kilometers an hour. Now, from 1 to 4, so I'll do that one in black. If you take this point at 1 and go to this point, 1, 2, 3, 4, that one, we're still traveling 200 kilometers only, but we've done it over 3 hours. So our average rate of change over that time is 66.7 kilometers per hour. I know we'd have to put another value up here. From 4 to 5, if I took that, and I'll do this in purple, from 4 to 5, we've only gone 1 hour in the horizontal distance and 100 kilometers. So our average rate of change over that time would be 100 kilometers per hour. So all the average rate of change is drawing that straight line between 2 points and finding the slope of that line. So you just find the slope of your line just like you would do before, change in y over change in x, rise over run. Now, what calculus is interested in is coming up with that instantaneous change. How fast is something going at a moment? It's not so interested in the average, but in the instantaneous rate of change. Now, the problem that happens is, let's say I've got part of a parabola here, and I've got the point A and the point B. Can you see that you could calculate the slope between A and B? Rise over run, no problem. Because according to what I've labeled here, if B has the points x comma f of x, and A has the points A comma f of A, does it make sense that this distance there is just the difference between your two y values? This is my large y value, f of x. This is my small y value, f of a. This will be just f of x minus f of a. If we had an actual part of a parabola over here, and you had, well, choose, let's say you had one point here that was 1 comma 3, and another point here which was 3 comma 7. Well, if I was making this distance here would be 7 minus 3, which would be 4. And this distance here would be 3 minus 1, which would be 2. And the slope of that line would be 4 over 2, which would equal 2. And so the horizontal distance here is just our x-coordinate here minus our x-coordinate there. Now, in calculus, you're interested in the slope just at one of these points. You're interested in finding what's that slope. So the idea is, well, I don't have 2 points with that slope. I just have this 1 point. But if I could bring this second point, like right now, can you see that this secant line that goes through here, that slope isn't a very good estimate for the slope of that blue line. They're not really close. But if I had chosen my B point here, that slope would be better. And if I chose my B point closer, that slope would be even better. And as I move that B point closer and closer and closer and closer, can you see that my secant line gets closer and closer to my tangent line? I've got an applet that I made right here. I don't know, I'll zoom in a little bit maybe. Doesn't make the words any bigger, does it? Okay. I'll tell you what it says right here. Right here it says the slope of the tangent, which is the red line at point B, is 5.4. And right now, the slope of my blue line is 1.07. They're not very similar. But if I take this point C and I move it closer, can you see that my secant line is getting closer and closer and closer to my tangent line? In fact, if I get them really, really close, the blue line and the red line are almost identical. They're still not perfect because you can see at the bottom that they're still a little bit off. So if I tried to move it even closer, here we go. And there's a little point in there. Now I'm really close to being the same. So as I can move that point closer and closer, I get closer and closer to the slope of my tangent. How do we write that? Well, the slope of my secant is my rise, f of x minus f of a, over my run, which is x minus a. If I want to find the slope of my tangent, I want my x value to get as close to my a value as I can. Go back to my diagram here. What I want to do is I want to bring this x value as close to that a value as possible. And if I do that, the limit will be whatever the slope of my tangent is. So I say the limit as x gets close to a, that will draw that secant line really, really close to my tangent line. And if I take the limit of that, then I'm going to get the slope of my tangent line. Now, with everything we've done with our limits so far, we find out, well, what happens when you plug in a for x? As x gets close to a, we divide by 0. So we have a problem. But that's what we were doing with our limits before, learning ways that we can simplify so we can figure out what that limit would be. These applets are other applets that work to show that same thing that I showed you with this one. It just allows you to drag a point closer, but for whatever reason they haven't updated my Java on my computer, so I can't show you those applets. Okay. So here's our first question. We've got a parabola, 3x squared minus 6x plus 1. We want to find the slope of the tangent line at the point 2, 1. So graphically, we know that this graph goes through the point 2, 1. If we wanted to, we could figure out the vertex for this one. The vertex happens to be at 1, -2, I think. Yes. The vertex is the sommet. Sommet. Actually, I'm going to just redraw that more accurately. There we go. So this is our parabola. And what we're interested in finding is at this point 2, 1, if we drew a tangent line, what would the slope be? Well, we know that our slope is rise over run. And the slope of any secant will be our rise, our difference in our y values, divided by our difference in our x values. And what we're going to try to find to calculate our slope is the limit as x gets close to a. And a can be any value. So in our example, we're wanting to find what the slope is as x gets close to 2. Because we're trying to find the specific point at the specific point 2, 1. So our x value is getting close to 2. F of x is our function. In this case, it's 3x squared minus 6x plus 1. And we want to subtract f of 2. Someone tell me the quick way to do f of 2? The long way to do f of 2 is to plug 2 in for x and figure out what it is. The quick way would just be to write 1. How did you know it was 1? That's right. The graph is going through the point 2, 1. They've already told us when you plug in 2 for x, this is going to be 1. It's not wrong to plug it in again to calculate what it would be, but that's a lot quicker. And then on the bottom, we are going to have x minus 2. So for those of you that have taken the IB math, you've never seen this formula in this way before, so this is a little bit new. Now, if we simplify the top, our slope is going to be the limit as x get close to 2. Why can't I plug in 2? Because right now I divide by 0, right? But the top, after I simplify things, just becomes 3x squared minus 6x. Any suggestions? We can factor the top, so our slope is going to equal the limit as x gets close to 2 of, can take out a 3x, leaving us with x minus 2. How nice is that? And so now you can apply that. What is our slope going to be? Just going to be 3x, and if you plug in 2 at that point, when x gets close to 2, it's going to get close to 6. So we now know that the slope of that tangent line would be equal to 6. Now the question said find the slope of the tangent line and the equation of the tangent line. So part 2 here, if we want to find the equation of the tangent line, well, anytime you want to find the equation of a line, you need 2 pieces of information. You need the slope of that line, and you need a point. So we know the slope is 6. Do we know a point on that tangent? Two and 1. So I'm going to show you 2 different ways you can find it. This is review. You probably remember both of these ways. 1, y equals mx plus b. If you use y equals mx plus b, you know that the slope is 6, so you can put that in for 6. And since you know that the point 2, 1 is on that line, you can plug in 2 for x, 1 for y, and you can solve for b. Solving for b will give you negative 11, so you know the equation of this line is 6x minus 11. That's using the y equals mx plus b form of the equation of the line. You might also remember the point slope form of the equation of the line. If you remember this one, you know the slope is 6. You know a point. And if you multiply this out, add 1 to both sides, you get the same equation. So you just have to say, well, which way do I remember better? Which way have I used more in the past? Have I used y equals mx plus b more, or if I used y minus y1 mx minus x1? And then you can choose whichever one you prefer. So I'd like you to try the next one on your own. I'll put up the answer in a second. So we want to find the limit as x gets close to 1, because 1 is the x value at the point that we want to find. Of course, here I did it the long way. I plugged in 1 into the whole formula, but you'll find out that that's equal to this whole thing here is going to equal 3, because when you plug 1 into the equation, they gave you the point, so you know that it's going to equal 3. Simplifying this and factoring, your x minus 1's cancel out, and we get a slope of 4. Once you've got your slope of 4 and you know that it had a point of 1, 3, using either one of those formulas that we looked before, either the y equals mx plus b or y minus y1 equals mx minus x1. Do you have one of those that you find easier to remember? The left one, y equals mx plus b. Did you know that the right one just comes from your slope formula? Your slope formula is rise over run. And if you took this and multiplied it up to the other side, you get this. The only thing difference is it isn't y2 minus y1 and x2 minus x1. Because you only know one point, you keep one as x and one as y and plug in the other point. But that's where that formula comes from.